So I'll talk a little bit about functional style in Java 8, just a little bit, but we'll then focus our time and effort on taking some code that we already have and refactor it to Java 8 and functional style. Well, one of the really cool things about Java 8 is Java 8 now gives us an ability to program in functional style. So what does it mean to be programming in functional style? Well, first of all, we can use the so-called higher order functions. Higher order functions are functions that can take other functions as parameters. So for example, let's say you are used to programming in Java so far. What could you do? You may pass an object to a function, right? You could do this already. You may create an object. So create an object within a function. You may return an object from a function. So these are the three things you could do when you are interacting with functions. You can pass an object to a function, you can create an object within a function, and you could return an object from a function. Well, when it comes to higher order functions, in higher order functions, you may pass a function to a function. You may create a function within a function. You may return a function from a function. So in other words, you're used to passing around objects to functions. Now you can pass functions around to functions. So this is a capability that you have with the so-called higher order functions. Secondly, in functional programming, we favor immutability. We don't take data and mutate it. Instead, we transform data. So you're taking some data and you are performing a series of transformations with it. You honor immutability as much as you can. You program in the so-called declarative style. What that means is you are going to tell what to do and not how to do it, and let the underlying libraries figure out how to do it. But this brings up to using lambdas. So what's a lambda? Well, we are used to writing functions or methods. In the case of Java, we mostly did methods. So what is a method? A method is a function, after all, which belongs to a class. It could be static or it could be instance. So while a function doesn't have a class affinity, a method often does. That's kind of how you know whether it is a function or a method. Until now, until Java 8, we couldn't create functions. We could only create methods, right? But in Java 8, we can also create functions. How? We'll see that in a minute. So a function is not affiliated with an object. We'll use the word function and method interchangeably. So for that, what we will do here is, what does a function have? Well, first of all, a function has a name, right? A function has a parameter list. A function has a body, and it has a return type. So these are the four things that typically a function has: a name, a parameter list, body, and a return type. Imagine you are boarding an airplane and they tell you can only take one item. So you're allowed one item. Of these four things, if I tell you can only have one, what would that be? The body, right? Because if I don't allow you to take the body of the function, the rest of the stuff is useless, isn't it? So the body of the function is absolutely one you take. Okay, I'll be kind to you. I'll give you one more thing to take it with you. Be careful. Which one? I'll give you the name. So what do you do now with these two? Will it work? No. That's it, right? Because this is the most important thing, would you agree? But what does this want? The input data, the parameter list. Without those two, you can't do anything. Hey, wait a minute. What about the return type? We can infer that based on this, right? We can infer this based on this. It's something you can figure out what it is, right? You don't have to say what it is. It's kind of known from the context. What about the name? It's anonymous. Who cares what the name is? And that's what a lambda is. So a lambda is an anonymous function which has two parts. A parameter list followed by this little arrow and the body. That is the signature of a lambda expression. So you have a parameter list and an arrow, and then of course you have the body of the function. It doesn't have any name, it's anonymous. Who cares what the name is? Plus of course the return type is inferred from the context. And as a result you don't have to specify what the return type is. So this is what makes a structure of a lambda expression. Streams are really very powerful construct. Stream is a flow of data. There's a difference between a stream and a list, or a stream and a set. A set or a list is a concrete collection. I can point to the memory and say, that's where the list is. That's where the data is. A stream is an abstraction. A stream doesn't have data. A stream is a collection of functions. You can take data and you can apply the collection of functions on the data. So a stream is an abstraction, not a physical data or a collection. And you can take a stream and perform a lot of operations on it. That's where you get the power of the stream to perform it. But one of the really beautiful things about this is that lazy evaluation. What is lazy evaluation? There is what is called the eager evaluation. Eager evaluation is you do things immediately when it's given to you. That's an eager evaluation. Lazy evaluation. You gave me this task, but I'll get to it eventually, right? So imagine your boss calls you on January the 15th at 3 o'clock. And the boss says, I've got a project for you. You got to work on it. And it's due on April the 15th. So what do you do at 3:15 on January the 15th? You know this project is due on April 15th, right? So as soon as you come out of your boss's office, you get back to your desk and you start working on it, right? Yeah. No. Because you, I know, I'm very confident, you will start on it promptly on April the 14th. Right? Because it is due on April the 15th. In fact, even better, there is something you know that your boss doesn't know. You're going to quit on April the 7th. Right? Why in the world would you get started on this, right? What is that called? No, it's called being smart, right? So laziness means efficiency. Laziness means efficiency, right? Oh, I'll do it later. And what are the three benefits? One, most important benefit, you may not have to do it at all, which is real efficiency, right? The most efficient is not doing anything, right? I mean, people say, are you resting? No, I'm just in idle state, right? This is the most effective state, right? Nothing happens. Then when you have to do it, you can minimally do it. Well, when you minimally do it, you don't do all this extra nonsense you would have to do. So both in life and in programming, it's a good idea to be lazy. And they say the most effective people are the lazy people, right? But there are other people who are like, keep doing things. Like, why are you just actively doing all this? Nobody cares what you do, right? Just relax. Only do what is necessary. That's the whole idea. Well, we'll see how we can apply some of these ideas together. So let's start with a little example. So here's what I want to do. Some of us start on greenfield projects. We work on new code. And when you start on new code, you could use some of these ideas. But a lot of us work on code that already exists. By the way, I'm not recommending by any means that you go to work and start changing all the code that is there. Right? That's not effective. That's not going to help anybody. So don't go off and say, oh, you know what, I found all these functional style. In the next 3 years, I'm going to change all the code. Hey, what did you achieve? I changed all the code, right? That doesn't buy anything. However, you're going to write new code. You're going to write new code in functional style. But along the way, often refactor existing code. You are there to fix a bug. You're there to make an enhancement. And on those occasions, we can say, well, I'm going to refactor this. I'm going to rewrite, make some changes to it. Might as well do a little cleanup, right? And then you can improve on those code to a functional style. So for that reason, I'm going to take some existing code. And I'm not, again, suggesting you change it just blindly. But if there's a good reason for you to get into a code like that, it's a good opportunity for us to improve it and make a change to it. Though I'm not going to show it to you here, there is one thing that can be really a true friend to us when it comes to refactoring. What do you think that is? Thank you. Automated test. When you refactor, you want to know the code still works. The other day I was refactoring a piece of code. Somebody had written an imperative style code. I looked at it and said, gosh, it's imperative. I'm going to make it beautiful. I'm going to make it functional, right? And I went and made sure all the tests passed. Yeah, it did. I modified the code to functional style, ran all the tests, and guess what? The test failed. There is no point in me saying, the test fails, but the code is beautiful, right? Nobody cares. So I have to make sure the test passed too. So I immediately rolled back my change, went back and really understood now what the code was doing, made a second attempt, refactored the code to functional style, and now the test passed. So anyway, one recommendation is, if you have enough tests, refactoring becomes easier. Let's take a first problem. The first problem I have here is this function called isPrime. What does isPrime do here? I'm not worried about the efficiency of this implementation here. I'm just interested in this particular code that's already there. It says, Boolean divisible is false. For I 2 to the number minus 1, if the number is divisible by I, divisible is true and break. If the number is greater than 1 and is divisible, return true, otherwise false. Right? And I've done this for multiple numbers. Run it. 1 is not prime, 2 is, 3 is, 4 is not, 5 is, 6 is not, 7 is. So the code works for at least these values. But it's an imperative style code. And I want to refactor this to more of a functional style. But before we do, let's put this in words. Let's put this in English. What does this code do? Don't tell me it tells me if it's isPrime, right? Yeah, sure. But how does the details of this? What does this highlighted code do? That's it. It tells you if a given number is divisible by what? Every number from 1 to, not 1, right? From 2 to 1 less than the number. Let's put that into a different word. 2 to 5, 2 to 7, 2 to 10. What is that called? Hey, there's a clue here. A range. Okay, given a range of numbers, what am I looking for? That given this range on the number, what am I interested in? Tell me that none of the numbers in the range divides it. English is your friend here, right? So now let's put that English into code. So I'm going to grab this one and highlight it, comment it. Return number is greater than 1 and And I'm going to say in here, return number is greater than 1, import java.util.stream.star int stream.range from 2 to the number. So we got a range of values, right? So return number is greater than 1 and int stream range 2 to the number. Well, it won't include the number because it's range not range closed. Dot none match. Nothing matches. Nothing matches what? Given an index I, number mod I is equal to 0. So you start thinking about this as what does this code do? Given a range of numbers, no number in that range divides this number, right? So you can start exploring these kinds of functions that are available. So here is implementation of the code in the top. The beauty of none matches, it'll short circuit. So it keeps going 1, 2, 3, 4, but the minute somebody matches, it bails out because you said nothing matches. Oh gosh, I found one that matches. And guess what? If one matches, it doesn't matter what happens to the next one, right? So it is efficient, it'll short circuit it. The only time it's going to go through the whole thing is if really nothing really matches. So from the point of view of computational complexity, it's no different from the top code, right? It's going to short circuit and bail out, just like we had a break. So the break is kind of inbuilt in here. We don't have to worry about it. So the code becomes very expressive, right? The code in the top, you got to step through the details of the code to figure out what it's doing. You got to keep going back and forth looking at the details. Whereas here, given this range, none matches this criteria. Oh, okay. So it may take a little while for us to get comfortable with the functional style, but as soon as we do, it becomes easier to read and understand the code. That's exactly what we are seeing here. Any questions before I move on? All right. So we saw how we could make use of this particular behavior. So we went from the imperative to a functional and declarative code. It's less noisy. Notice we did not use any garbage variables. These things are called garbage variables. You assign them to variables, and then you keep changing the variable, then you come back and check the variable. In fact, these are garbage variables. What do you normally do? You give them very cryptic names for it. You call it D, K, P, T, whatever comes randomly in your mind, right? You just put it. Why? Because you say, I don't care about you, right? So we just throw some names on it. Whereas here, we don't have a garbage variable. That kind of is not necessary because the code becomes a lot more expressive in what we do. Second, we used higher order functions. Notice we passed a function, we know this as lambdas, and we passed a function to the none match function. None match is a higher order function. Unlike range, range took what as a parameter? 2 objects. A primitive 2 in this case, or integer, and the number. Unlike range, none match says, I'm going to take a function as a parameter, right? So that's why none match is a higher order function, while range is a general method or function. Moving a little forward, I want to, yes please. Yep. Oh, no. You don't want to. No. Yes. You don't want to, but this voice in you keeps telling you to do it. Write another method and call it. Write another method and call it. In fact, let's step back for a second, right? Just step back for a second. Don't worry about it right now at the moment. You got some kind of a work being done. We'll call that as, lot of work. On what? On the number I and number, right? Even in this code in the top, right? You don't want to put 200 lines of code in there, in the if statement. That is called being very cruel, right? So what would you do? You probably will write this lot of work as a method already. Well, you just come and call the lot of work here. That's it. So it's no different from that. Yeah, curlies, no curlies. That's really ugly code. We don't want to do that. Yeah. This guy here. Yeah. So this guy is, what is it returning, a true or false? Right? So it's a predicate. In fact, because it's on an int stream, it's going to be int predicate. That's what it's going to be. Here's another little way to try this. I'm going to do absolutely something stupid, right? I'm going to say hi right here. And it says hi is not a int predicate. That's another way to easily find out. So do something stupid and compiler yells at you. It's like, okay, got it, right? So it's int predicate. That's what it is. Yep. Cool. Nice questions. Good. Well, next problem I want to work with. What I want to do here is this beautiful code. It says search word. I want to search for a word called localhost. Where do I want to search for it? In this file called etc/hosts. Long count equal to 0. Buffered reader, new buffered reader, new file reader. Then string line equals to null. Buffered reader dot read line. If set it to null. If that is not equal to null. Isn't that so beautiful? How many of you love writing that code? Not a single person? Okay, he's taking pity in me and saying, right? Do you really like writing that code? You need help, my brother. That is really, really sad code, isn't it? Why? Null is the smell, first of all, right? If you're writing this code in the laptop, the minute you type null, you put it away, right? I don't want to keep it on my lap. So that null is really smell. And then you set it to line, and then you check if it's null. This is like totally low level, right? That's like doesn't make fun at all. Then you say, if it contains the search word, then increment the count. And then you keep looping, and then you say, word is that. So this seems to be really so low level. What can we do about it? Once again, put it in words. What are we really doing? If those of you standing want a seat, there's quite a few seats in the front. You're most welcome to walk to the front. So what are we going to do? So in this case, of course, we think along the lines of streams for a minute. The JDK has several methods that return streams to you. And the minute you get streams, there are certain things we can do with streams. We can do operations at the collection level. We can say, given the stream, we can filter out elements we don't care about. We can map elements, and so on. So what I'm going to do here is, let's try this. First, run this. When I ran, it says the word localhost occurs 3 times, it says. I want the same result for the given input, right? The word localhost appears 3 times. But what are we going to do instead of this? Let's refactor this. So we want a count in the end. But where is it going to come from? We're going to say, first of all, over here, files.lines. Let's start with that. Files.lines, well, what is this going to give? It's going to give us lines. But where is the files I'm going to start with, right? I need to be able to get the lines out of it, but I need to do a files.get. Well, I'm going to get the file itself that I'm interested in. So files, and I'm going to use paths. Paths.get is going to give us the actual path where the content is. So we can ask for a few interesting details from these classes. But the most important revelation here is that there are functions that are going to give you streams. So let's go to the files class for a minute. If we go to the files class in Java 8, change that to Java 8, what does this give us? Well, if you look at the files, and I'm interested in this thing called lines, as you can see. But the most important detail here is notice that lines is returning a stream of string. Well, that's awesome, isn't it? And that's taking a path. But for the path, we can use the paths to get it. So let's try it. So files.lines, paths.get, and what is the path I'm interested in getting it from? Well, the path for that is this guy here, path. So I'll give the path over here. So this says, I'm going to give you a stream. Where is the files coming from? Java.nio, and that's where we're going to get the files from. Then, that's a stream, isn't it? And once I get a stream, I say filter. And what am I interested in really? Right here, right? Line contains search word. So given a line, line.contains the search word. Same thing as in line number 17. But then I want to count, dot count, and get the count, and this is going to be long, count is equal to, and store the result of this into it, right? So what is this going to be? Files. And we're going to get the value. Where did the paths come from? So this is going to be java.nio. Is it file? Dot star. Here we go. So now that's the re-implementation of that particular part. So we are saying files.lines, and then once you get the lines, it's a stream. Once you get the stream, you can do a filter, and once you do a filter, you can count on it. So all the chunk of code in the top becomes the code in the bottom, right? The result is still the same as it was before, but we are using this. In fact, this is the funny part is, if the code you had as a bug, the code you refactor better have the same bug too, right? I'm working on a project right now. We are refactoring code. And I asked my client, well, good, I'm glad you're refactoring the code. But how do you know that your original code is correct? That evening he replied back saying, okay, you're right, we did find a bug. And we promptly reproduced it in the new code. Well, you want to keep the behavior the same for a while, right? And you want to completely come and attack that separately. In this case, there's a flaw. It actually doesn't count the number of words. It only computes the number of lines rather than the words, right? So if you really want the words, you got to check for each word after splitting it. And you have to do that here too. But I'll leave that as a homework if you're interested in that. And I'm going to show you a concept a little later on that you could use in this case. Again, from imperative to functional style. No explicit mutability, right? Look at this part. We constantly mutate the poor line. And then we assign the value to it and check it. We're not doing any mutability. Likewise, look at count. Count was constantly being mutated. Here we're not mutating the lines count explicitly, right? And then of course, we're using streams and filter. So the next model of the story here, when you're given a problem, see how quickly you can get to a stream. Because once you get a stream, you can do filters and maps and reduce and stuff like that. So that's one thing to look for, is how can we get to the streams. This one I showed in the previous presentation, but let's look at it again in here, for those who were not there. For grouping, this can be a really nice, powerful way to do this. So let's take a look at this example. I've got this thing called scores, and I got scores for a few people. Jack, Jill, Tom, Darla, Nick, and Nancy. Some of them have the same score, some of them have different scores. I got a function called group by score. What does this do? It groups people based on the score. Tom and Nancy have 11 points, Jack has 12 points, Darla, Nick, and Jill have 15 points. So I want to do this grouping. Well, to do the grouping, what have I done? Here's the code for grouping. I have first of all created a map. I go through one element at a time. I take a name, get the score for the name. I create an empty list. I get the list from the collection, add it to the list. If it is not there, I create a list, of course, and then I put it back into the collection again. That's a lot of work, isn't it? But what is the real purpose here? The purpose is to get a list, a map, where the score becomes the key, and the value is the list of names of people who have the same score. This is where we can effectively use collectors. So if you look at the collectors, collectors is a utility class that contains a bunch of functions that are helpers for the collect method. So this is a very powerful, if you make a note of this, it's very well worth spending an afternoon just browsing through the collectors class. You will come across so many methods that are so intriguing. One of the most powerful utility classes in Java 8. So what I want to do here is I want to return this by score, obviously. But to do this, again, we will start by looking at the input given to us. So return, the input given to us is the scores. So scores dot. I'm interested in going through the scores, but I'm interested in parsing through what? Well, in this case, if you look at our collection, in the end, we want to return a collection of scores as the key and the names as the list of values. So what we could do here is we could take one key at a time. So we could say keys. That's a set, as we know. So that becomes the set. Then what I can do is I can do dot collect. So we could call a collect method, but in this case we can say over here grouping by. But what do I want to really group these values based on? I want to group the values based on the score for the given key. So I'm walking through the keys. I am saying I got Jack first of all, then I have Jill, I have Tom, Darla. But when you take a Jack, well, let's step back. Again, think a little bit in a higher level. So what am I really trying to do here? I've got a collection of people's name. I got Jack, Jill, Tom. Let's start with only these three people, Jack, Jill, and Tom. So what am I going to do? I take Jack, and what am I going to say? Oh, Jack, you're going to be in bucket number 12. Jill, you go into bucket number 15. Tom, you go into bucket number 11. Darla, you're going to go into, hey Jill, make a little space for Darla, please. Same bucket as where Jill is, right? So in other words, you're going to put them into buckets. That's exactly what grouping by does. Grouping by creates these buckets for you. But you got to tell it, create a bucket based on what? I want to create a bucket based on the score. So grouping by, in this case, scores.get. And on get on what? Well, we are going to take the given key, isn't it? And this is going to be based on the given key. So you're going to create this based on the key. Cannot find symbol key. What is that called? Given the map, I want to find the key. Key set. Ooh, key set. And so in this case, of course, little problem here. It's unhappy. Let's actually give the type here real quick. String. Because the keys are of type string, isn't it? So let's go ahead and give the type and see what it says. It says, cannot give you the result here. He's obviously having a little trouble. Let's see what the return type here is. It's a map and a list of string. Oh, of course. This is going to create these into a bucket, all right, but we are interested in returning So if we put a little type here, it may be a little bit more useful. Let's take a baby steps here before we come back to attack that. So map string, list of string, map integer, right? Integer, because that's what we are trying to return, map integer in a list of strings. And we'll call this as result is equal to, and here is the scores dot key set. So we take one key at a time. And then we say dot collect. And in this case, grouping by. And what do we do here? We're going to say, given a key, which is a string, return to me a scores dot get for the key. And then, of course, return the result. We're going to still get the error, but we'll figure out result. So in this case, of course, what does a grouping by say? Grouping by says, I'm going to give you the buckets to put it on. So in a sense, you can say, given this particular value, get me the value for this. But we also want to say what to put the resulting value into, right? So in this case, we are trying to take these scores. This guy is the score. Here. But this is the list of the items I'm interested in. If you work with the values, what happens? The values are going to be these guys. That's not going to help. We'll see if we can work with the entries instead, right? So, still not happy. Let's go back and take a look at the grouping method. What if I can give him a pair of values to work with for the grouping? So collectors, remember, of Java. So going back to the collectors, let's look at the grouping by. So grouping by, and the grouping by says, you can give me the mapping function, what I need to group based on, but it can also give me a little bit of a help as to how to deal with the second transformation. So let's go to the grouping. Where's the grouping? Right here. So the first, this is the simple form. It takes a function which says, given the key, what do you want to classify based on? But I can also give you another collector, which is a collector downstream, which can take the values and collect it into something else, maybe to a list, if you will. And I can transform that further into a list of values. So what collector do I want to use here? Maybe to a list, all the elements that I get right now. But in this case, though, what is going to be the list of values that I'm going to collect into? So I got the name, but I want to put it into a list. So let's see if we can give it to list here. And so let's see. If this is going to be the end of the grouping, isn't true? This is the, there we go. To list. So, yeah, sorry. So that's still not working. So I'm stuck here. So this is a list. He said, oh, yeah, you are correct. Because it's a set, isn't it? How did I forget that? Yes, that's correct. So you want to convert that to a stream. It's weird that it was giving an error on collect instead of saying there's no collect method. Weird. Okay, there we go. That was the problem. Thanks for fixing it. Kudos. So yeah, the key set should give you a set, and you want to collect it to a stream. We can do one more little optimization here. We can simply return the result from here. So thanks for your help on that. So I return it from here. We can do this. But looking at this, notice this says, given a key, call the get and pass the key. We can make this a little bit more expressive. We can say score, : get. So we can minimize, this becomes a little bit easier to read also. If you notice, given a collection of keys, get me a stream from it, and collect it, grouping by the result of the get method. So this gives you an ability to transform this into that list, or the map rather. But the beauty of this is we took that much code, which is imperative, and with some help, of course, we transformed it to something much simpler here, as you can see, right? So that's basically what grouping by does. It can put these into different buckets, and that's what I was trying to get to, is to put these into these buckets based on the score value. So we went from a verbose code to a fairly concise code. We went from something that is very verbose to something highly expressive, right? We're also in a declarative form here, rather than the imperative style we saw a few minutes ago. And then we are using a very specialized function here, which is the grouping by function, for us to do the work. So that's basically one other example of refactoring technique. But when you look at a problem like this, you say, what are we trying to do? And the key here is to be able to observe the problem and realize you're trying to put them into different buckets, which is you're trying to group them. You're trying to group them based on the score. And the minute you, again, formulating this in English, right, is one of the first steps. What are you trying to do? I'm trying to group these. Oh, that's a clue. I'm trying to use something like a grouping by or group by function. So formulating the problem is a very important step. If we cannot formulate the problem into words, no amount of API in front of us is going to help us. But once we formulate it, then it gives you a clue as to, because these method names are very highly intuitive for the problem, but once we know what the problem is, to state it in a way, it's easier to figure this out. Let's go a little further. In this example, what I'm going to show you here is, let's take a look at this. This is one massive code. If you notice, in this example, I have a very highly bloated OO code. And I'm going to convert it to a functional style. First of all, I have something called an applicant. Again, this is purely a fake example, right? So don't read too much into it. But it's an applicant. It's got is credible. This applicant is credible. I'm getting a credit score for this particular applicant. It's 700. I mean, in reality, of course, you will pull stuff from a database, what have you, right? But the point is, I'm just faking some data. Employment years. This person has 10 years of employment. Does he have a criminal record? He does. Should have been in politics. So we kind of have the object, right, the applicant, on our hand. Then I have an evaluator. Notice evaluator is an interface. It says I have an evaluate method which returns a Boolean given an applicant. It clearly is an interface, no implementation. Then I have a qualified evaluator which implements the evaluator interface. Its evaluate says I'm going to return to you whether it's credible or not. Likewise, I have a credit evaluator. Says I'm going to check the credit right there. Credit score of 600 or higher. Then I have a employment evaluator. If you have no work history, that's still cool, greater than 0. Criminal records. If you had criminal record, yes, otherwise no. Then I have a chain of these, evaluator chain, which says when you call on me evaluate, I'll call the evaluate on the next one in the chain. If you look at this code, finally, we create an applicant, we call an evaluate method. The evaluate method takes an applicant and takes an evaluator. But here we say new credit evaluator, new qualified evaluator. Similarly, employment and qualified. Similarly, criminal employment qualified. So we're putting multiple combinations together. About 99 lines of code, as you can see right here. When you run this for this example, it says accept, accept, reject, reject. That's what we want as the output eventually, right? So the result of evaluating the application of the first one, only on the credit and qualified, accepted. The person has credit, is qualified. Second one, credit and employment, has credit, employment is good. Next one, criminal employment and whatever that was, rejected because the person has criminal record. Last one again, criminal credit in employment and qualified, still rejected because the person has criminal record. So we want to be able to implement this, but in a much more effective manner. So how do we do? Couple of things. Let's start with the interface. When you look at the interface, evaluator, when you look at interfaces, look to see if your interface has exactly one abstract method. If your interface has exactly one abstract method, that interface is also known as a functional interface. So a functional interface has exactly one abstract method. More important, when you have a functional interface, there are three things you can pass. You can pass an abstract, you can pass a class, that object that implements that interface. You can pass a Lambda expression, or you may occasionally pass a method reference if it fits. But if you really look at it, this evaluator is actually very much like something already in the JDK, which is the predicate. Because a predicate takes an object, returns a Boolean too with a method called test. So we can actually rework this code to get the same result. But in order to do that, I'm going to temporarily comment out this part. We'll come back and fix it. But I'm going to start with the evaluate method. The evaluate method takes a predicate. Instead of the evaluator, I'll say predicate of applicant evaluator. Within the code, evaluator.test instead of evaluate. If it is accepted, accept, otherwise reject. That is all the change I made so far. Then I'm going to go over to evaluator, and I'm going to get rid of this evaluator. That's gone. Then I go up here to the qualified evaluator. I will create a class called interface called evaluators with a plural, just for a minute. Look at this guy here. What does he do? He says, I'm going to check for credibility. So I will create a public, static, and I'll create a method called isQualified for the applicant. And what will I do here? Return, in this case, I'm going to say applicant.isCredible. So I converted this class into a method in the interface. The chain is gone. I don't need it. The credit evaluator says, I'm going to check for credit score being greater than 600. So I'm going to say public, static. So in this case, this is going to be static. And what is this called? Credit, right? So evaluate credit. Given an applicant, let's call this something a little different. Is credit worthy? How about that? Then I'm going to say return applicant dot get credit score greater than 600. That means we converted this class into a method. What does this do? Employment. Static is employment. Let's call it as employment, so is employed or has been employed, right? Again, an applicant. And what does this do? Return applicant dot get employment years is greater than 0. Finally, the criminal record. So static is not a criminal or doesn't have a criminal record, however you want to phrase it. Don't hold me to the names here. So return applicant dot, what did we call that one? Has criminal record and doesn't, right? So let's see how this is going to work. We got rid of most of those things. Now we can come back here. So the evaluator's interface has these static methods. You could put them elsewhere too. You don't have to put this in the interface. But then let's start with this one. evaluate applicant. We want to check the credit evaluation and the qualified. How do we do that? Well, we could take these as predicates. And if we take these as predicates, we can then work through this a little differently. Let's go back and try this. So I have the qualified, right? That's what I have here. Credit and qualified. So let's go to qualified. Is qualified, what does this return? Maybe I don't want to return a Boolean. I left out the type here for a minute. I'm going to say predicate applicant is qualified, and I'm going to say here, move this applicant from there into here. So I can say applicant arrow applicant is credible. So that is our first thing. Likewise, we can say I have to return a predicate for is creditworthy, but the way I'm going to do that is I'm going to take an applicant here as a parameter and return if it is that one. Again, we are moving the parameter from there to here, right? We're postponing receiving that one. Similarly, I'm saying is employed. Well, for this one, I'll take the applicant from here and move it to here too. So each of this become a little predicate being returned. And finally, predicate applicant, and I don't have to specify the applicant here anymore. Same token, we simply say given an applicant, return that. What's the benefit? The benefit of this is I can go back here and say evaluate applicant. Well, notice a credit evaluator. What is credit evaluator turned into? It's turned into is creditworthy, isn't it? Is creditworthy dot and what's the next one? Qualified evaluator. That is qualified. So I can try to pass these two in here and say I can use that one. Where's the predicate coming from? That is coming from import java.util.function.star. That's where the predicate is sitting. And of course, where is these guys coming from? These are part of evaluators, isn't it? So I can say in this case, this is applicant evaluators dot is creditworthy, evaluators dot is qualified to get the value. So we are turning that into predicates rather than having separate classes. But the beauty of this is we can combine using the predicates. Benefit, let's go to the next one. Evaluators, this is a credit evaluator. So evaluators dot is creditworthy. And what are we going to use next? Employment evaluator. That is evaluators dot. For the employment we said is employed. And then finally dot and what's the next one? Is qualified evaluator. And that one we called as is qualified. That is coming from evaluators dot is qualified. And as a result, we can close that one. So that says accepted too. Now we can easily modify this guy here. So this becomes applicant. This is evaluators dot criminal. So for the criminal it is called is not a criminal. So is not a criminal. And then and what do we go from there? This one says employment. So evaluators dot is employed, and then this is going to become qualified, and that is going to be is qualified, and this is of course evaluators. You can do a static import, then you don't have to see evaluators so many times, right? So you can minimize the effort a little bit further, and that's rejected. And then finally, of course, for the very last one, we can say, well, given these values, I first want to evaluate the criminal, which I did, then the credit, so we will say the next one is creditworthy. The third is, the third is employment, so is employed, and then finally, the next one here is, and then, so this is going to be dot and. This is going to be evaluators dot is qualified. So you can start combining these functions very effectively based on what your needs are, right? And we came down from 99 lines of code to about 65 lines of code, right? So what did we do in this example? First, we removed a bloated OO code. We are just using predicate and we are combining predicates together. We're using higher order functions, we're using composing operations by forming the chain, and we can do quite a few interesting things. Well, I'm going to talk about one more. I'm going to skip this part, and I'm going to get to this one. And, well, okay, I'll talk a little bit about the part I'm skipping. We have been looking at filters and maps and such, but there are times I get often emails from people saying, okay, I get it. I can use filter, I can use map, but I have a problem here at my hand, I don't know how to solve it. Almost always, when I look at the problem, it tends to be a place where they could use flat map, and they haven't quite figured a way to use flat map. This happens quite often. I'll probably reply to one email every month like this, where somebody says, here's my problem, how do I solve it? And then use a flat map and say, here's how you can solve it. So that's what motivated me to provide that, but I don't think we'll have time to go into it and do justice to it. But when you download the code examples from here, you can take a look at it and play with it. But I'll come to something else which is equally important, I think, maybe a little bit more common. So this problem I want to take up next is this one here. Okay, sure, we have the is prime, but look at this code. Compute sum of square root of primes. Let's look at the code. What is it doing? Index is start, computed count is 0, sum is 0. Then it says if it's prime, add the square root to the sum, increase the computed count, and then index plus plus, right? So if you look at this code, that's a lot of work, a lot of things going on here, right? It's clearly imperative style in style. But that's going to be quite a bit of effort to understand. You first have to initialize these values. Then you check, compute count is less than count. You have to wonder, less than or equal to. Then you check if it's prime. Then you do the work. Then you increment the count. Whether you increment the count or not, you got to increment the index outside. So that's way too many moving parts in this code. But one of the really beautiful things about streams is, I mentioned that streams are lazy. So what does that mean by streams are lazy? Well, to understand this, let's start re-implement this code. Well, first of all, run this. It tells you 770.3433, blah, blah, blah. We want to get the same result. But let's refactor this. We'll first of all say stream.iterate from the given number start, given an element plus 1. Just look at this one line for a minute. This is called an infinite stream. It says I'm going to start with start, and it'll be start plus 1, start plus 2, start plus 3, start plus 4, start plus 5, and it keeps on going. It's an infinite stream, but how in the world can a stream be infinite? The only reason a stream can be infinite is this is evaluated lazily. It says, I won't really do this until you really ask me to do the work. If it is not a lazy, if it's eager, what would it do? The minute you call that method, it's gone. And it's going to be running forever. You will never get to the next line, right? If this says, I'm going to postpone the work. I'll just give you back a stream, and I won't do that work until you really ask for the result, until you demand it. Then you say, all right, but notice, I don't want all the values. I only want the primes. Dot filter sample is prime. Thanks, I don't really want the prime. I want the square root of the prime. Map math square root, right? Well, well, thanks, but I don't want the square root. I want the sum of the square root. Okay, so map to double dot sum. Oh, wait a minute. This is a slippery slope because this is going to be infinite. I don't want all the values. Well, what do you want? I want only count number of values. Oh, dot limit count. Right? A limit how many? To, what was this? Yeah, count. So notice what we did. Iterate from start, get me only the prime numbers, get me the square root of the prime numbers, but only count of them, and sum it. So when you run the code, it produced pretty much the same value, isn't it? But look at these two pieces of code. Which of these two is expressive? The one in the bottom, isn't it? Because the one in the top, you got to keep going back and forth. You got to stare at it. You got to say, what does this do? Why are we incrementing in the right place? Should you do this here? Should you do that there, right? That top one takes a lot of effort. The bottom one reads like the problem statement. Given all the values starting from start, get me only the prime, but the square root of them, but only count of them, and total it. Right? So we are going from a very cryptic code to a clear code, very concise. We're using an infinite stream, but we have also used lazy evaluation. This only works because the evaluation is lazy. If this evaluation were not lazy, we wouldn't be able to use this. That's one of the charming features of Lambda. Lambdas are lazily evaluated, and that's why that comes in to evaluate only when it's needed, not other times. So we saw about 5 different examples here of taking existing code, which is imperative, old-fashioned, to converting it to functional style, which actually is older than the other style, but it just not been adopted so widely. If you're interested in the code examples I showed you here, you can download it from my website on the downloads link. Hope that was useful. Thank you.